In this next video, we're going to look at a handful of solution properties. We're going to start out first by discussing electrolytes, but let's define what an electrolyte is. So an electrolyte you may have heard of in terms of like Gatorade or Powerade, things like that you drink when you work out, but the scientific term is a solute that when dissolved conducts electricity. And I know it seems weird that you hear about this often with sports drinks, but this actually is a pretty important property of how our bodies behave. We need to move ions around, and as we work out, we actually sweat out a lot of our ionic compounds, these salts, and we need to replace them by drinking electrolytes. All right, a non-electrolyte is basically something that doesn't conduct electricity. All right, so let's take a look at an image here that I think does a pretty good job of showing what I mean. And this is an image just from our textbook. And over here on the left-hand side, you can see this light bulb turning on pretty strongly over here. So this would be classified as a strong electrolyte solution. Right, so this solution that's down in this blue area is going to be a really strong electrolyte because it's allowing current to flow through the liquid, the solution. In the middle here, you can see this light bulb's kind of on, but it's not great. This would be called a weak electrolyte. And then over here, you can see that this solution's not really conducting electricity at all, and this would be a non-electrolyte. So as you can see, it's kind of a series of grays. It's not binary. It's not that something's either an electrolyte or not an electrolyte. Instead, you can have some that are really strong, others that are kind of in the middle, and then some that really don't do any conductivity at all. Okay, so let's think about this in a bit more detail. And I want to take a look at what's in this solution. Okay, and in this solution, it's kind of interesting. I'm pretty positive that they dissolved copper sulfate, which is CuSO4, into water. So if you dissolve this in water, it's aqueous, right? So we can just say AQ. And when this dissolves, you get copper 2+ as an aqueous anion, or sorry, aqueous cation, plus you get 2 chloride anions that are aqueous, right? So it completely dissociates into these ions. In fact, I'm going to just squeeze this down so we have a little bit more room to work with, but you're welcome to orient this however you want in your notes. Okay, so we've got our copper sulfate over here. And then over here, my guess is that this is acetic acid. So this is going to be CH3COOH aqueous, which really doesn't form very much ions. So it might do a little bit, and to show this, oftentimes we do this double-headed arrow, where on the top we might have a little arrow going that way, but the most of it wants to stay over on the original starting side. These are called equilibrium arrows. And it could, in theory, react to form some anions that are aqueous, plus some protons that are aqueous. But in reality, we're not going to form very many of them. Okay, and then last but not least, we've got this one over here. And I'm just going to kind of tuck this underneath. This would be something like ethanol. So CH3CH2OH. If we have this aqueous, it does not dissociate one bit. All right, it just kind of hangs out by itself. So the key difference between all of these is that this dissociates completely into ions. So you put it in, all of it breaks apart, and you've got hydrated ions floating around. Over here, you can see that this one doesn't really form very many ions. So only dissociates a little. That's why it's a weak electrolyte. And then this one over here does not dissociate at all into ions. All right, so that's the main idea between strong and weak and non-electrolyte solutions. And I think it's pretty neat that we can actually check this by using some light bulbs too. It really goes to show that the theory does match our observations, which is neat. All right, so the next section I want to look at, these are called colligative properties, and these are a bit different. And colligative properties are properties that are dependent on the concentration of a solution. Actually, let me put this up here. All right, so let's see what some of these colligative properties are, and some of them you may be pretty familiar with. So let's pull up table 7.5 from your book. Actually, this is the wrong table. Let me get rid of this one. 7.5, here we go. And this has some common colligative properties of pure solvents and solutions, right? So if we think about these things over here, vapor pressure, boiling point, and freezing point, they're very dependent on the concentration of a solute. So one of the common things you may do in your kitchen is if you're ever boiling water to make pasta, it often says to add salt. Part of that is for flavor. And then the other side of it is when you add salt, you actually get a boiling point that is higher than pure water. So if you go and check it with your thermometer, you may notice that it boils above 100 degrees Celsius. Vapor pressure and freezing point are actually the opposite, where vapor pressure and freezing point will drop. So if you think about adding salt, like kitchen salt, to ice on a stormy winter day, that will actually lower the freezing point of water, which might help dethaw your front steps or something like that. So it's kind of a unique thing. It depends a lot on the concentration though. Okay, so let's go ahead and take a look at how this all works. And we can calculate the freezing point depression or the elevation of boiling points by using a pretty simple equation. And so this is an offshoot of these colligative properties, but now we can apply math rather than just generic abstract terms. But they both use similar equations. It basically says is that the change in freezing point or boiling point, we call that delta T, is equal to N times K times M. So let's just define all of these. So this is the difference in freezing or boiling point relative to pure solvent. All right, so if we're dealing with water, we'd be saying, all right, is the freezing point, if it's lower, how much lower than 0 degrees Celsius is it going to be? Or if we're dealing with boiling point in water, we'd say how much higher than 100 degrees Celsius would it be? But it's all relative to the pure solvent. All right? And then N is going to be the number of species in solution. In fact, let's do this, number of moles in solution. All right, and I'll break this down and show you an example problem. And then K is going to be a constant. We have to look these up in a table, and don't worry, I'm not going to make you memorize any of these. We'll practice by looking up some on our own. And then M is a little bit different. This is called molality. The book says that molality and molarity are essentially the same thing. It's kind of true at low concentrations, but let's try to be more specific than the book. I'm a chemist and I'm just built that way. So molality is really similar to molarity, where you take the moles of the solute, but instead of dividing it by liters of solution, you do it by kilograms of solvent. So it's pretty similar for most circumstances, but it is slightly different in terms of the definition. So let's practice this. Okay, and let's do some calculations. And let's say that we have 155 grams of calcium chloride dissolved in water. And we're going to dissolve it in 1.00 kilograms of water. What is the expected boiling point? Or actually, let's do freezing point. You can do boiling point too, but let's just do freezing point for this one. Okay, so let's break this down and let's think about the overall chemical equation. So if we have calcium chloride in an aqueous solution, it will dissociate. Specifically, it'll dissociate into calcium 2+ cation. And then each of the chlorines will be dissolved. So I'm going to draw this a little bit differently, but we're going to get 2 of these, right? Oftentimes we just show a coefficient 2 in front, but I'm going to break it down just for emphasis. And the reason I do this is this clearly shows that we have 3 moles of substances in solution, because this completely dissociates. So that's going to be our N value. Okay, so now we can go ahead and start working with our equation, and we can say delta T is going to be equal to N times K times M. Okay, and we said that N is going to be equal to 3. That's where we got this value from. If we look at the K for water, we need to look up specifically the K value for freezing. So let's go pull up a chart. And here's a K value for freezing. So what I would do is I would go over here and I'd find water, and I'd say, well, the freezing value, that's Kf, is going to be 1.86. Okay? So I would go and say this is going to be 1.86. And the units are a little bit weird. It's going to be degrees Celsius times the moles of solute over the kilograms of solvent. Okay, so this is going to be our second value that we found here from that chart. All right, and then the last one we need to figure out, oops, sorry, I actually got these flips. It should be kilograms of solvent on top over moles of solute. I always flip that on accident. Sorry about that. All right, so we've got our K value in there. Now we need to calculate M. So this would be moles of solute per kilograms of solvent. All right, so let's try to figure out the moles of solute. We know we've got 1 kilogram of solvent. Okay, so down here, I'll just do another conversion. moles of CaCl2. And we know that for this, we can find the molar mass by saying 1 mole of CaCl2 is equal to, what would that be? 110.98 grams of calcium chloride. And we'd find that from the periodic table by adding up the mass of a calcium atom plus the mass of 2 chlorine atoms. Okay, and up here it said we had 155 grams. Okay, so 155 grams of calcium chloride. We want to cancel out grams, so I put this 110.98 grams of calcium chloride on the bottom. Sorry, that should be a G. And 1 mole on top. And this would tell us how much we've got in moles. Okay, so if we do this, let me type it into my calculator really quick. I've got 155 divided by 110.98. I'm getting a value of 1.40 moles of calcium chloride. All right, so we're almost there. Now we need to just kind of plug in all of these numbers. We know that we've got everything we need. Okay, so up here, we'll just copy this back down. We'll say delta T is equal to N times K times M. And we said that N was going to be equal to 3. That's the number of ions we made. K, if we looked it up, was going to be 1.86 degrees Celsius times kilograms of solvent over moles of solute. And then we said that molality is going to be our moles of solute, which is 1.40 moles over our 1 kilogram of solvent. All right, so let's double check that everything cancels. This number right here had no units. We were just canceling it, but that's okay. We could cancel out our kilograms of solvent right here and here, and then we could cancel out our moles of solute right here, and we'd be left with this, just our temperature unit left over. So this is 7.81 degrees Celsius is what I'm getting. Okay, and what this means is that this is going to be lower than normal. Okay, so let's break this up even further. If we think about the freezing point of water, the freezing point of water is normally 0 degrees Celsius. So in this case, the freezing point would be expected to be negative 7.81 degrees Celsius. And that would be my final answer for this problem. All right, I hope that makes sense. I know it does require a fair amount of math though. All right, one last thing that's related to colligative properties, and this is osmotic pressure. And I think it's easiest to explain osmotic pressure through a series of different images here. So let me copy one over. And the first one's kind of a simple one. So let's imagine that we have a beaker and we put a barrier in it. And then on one side we add a bunch of sugar, and on the other side we just have pure water, right? So if it's a really solid barrier, the sugar can't move to the other side and the water on this side can't move to the other side. Basically everything's stuck in one half of the beaker, right? But if we remove that barrier, what will happen? Well, eventually things will start to settle out and diffuse across both sides, right? So if we were to add the barrier back in, we could end up with an equal amount of sugar water on this side as this side, right? It just kind of makes sense that things will diffuse until we hit an equilibrium. Well, osmotic pressure is kind of related to that. And let me show you a different scenario. Okay, and in this scenario, instead of having a really rigid barrier, we have a different type of barrier. We've got what we call a semi-impermeable membrane. So in this case, we've got pure water on one side, a sugar solution on the other. But what happens is this semi-permeable membrane allows solvent through, but only solvent. Meaning the sugar can't move, but the water can. So then the question is, well, what would happen? Well, things want to be in equilibrium, right? So it's going to try, or at least attempt, to make the concentrations on one side of the beaker the same as the other side. So what will happen is the water from the pure side will sneak through that membrane, that semi-permeable membrane, and lower the concentration of the sugar solution on the opposite side. But eventually it will start to sputter out, right? We're not going to just completely empty this side, because instead we've got the force of this column of the water essentially pushing down, which is counteracting the force of the water trying to get through the other side. So this is basically at equilibrium right now. This column of water right here has a lot of force pushing down that's going to counteract the force of the water trying to sneak through. All right, I hope that makes some sense, but let's go ahead and try to define some of these terms, and then we'll come back to this. So osmosis is the process of the water sneaking through. This is the process through which solvent, in this case water, flows through a semi-permeable membrane to the solution side. All right, so that's the water sneaking through. That's just called osmosis. But then we also have to describe something called osmotic pressure. And osmotic pressure is kind of interesting. Imagine that we have to push down on this until we get back to a level where the water is equal. In fact, I'll just do that over here. So push down. This would be pressure. Until these two are now equal again. So I'll just go ahead and do my terrible art drawing. Oh man, that is bad. Where these two volumes are now equal on both sides. This push down pressure that we need to get things equal again is called the osmotic pressure. All right, so let's define this a little bit more carefully. This is the hydrostatic pressure required to prevent that flow. Of solvent through a semi-permeable membrane. So like I said, it's the amount of force you would have to apply to that opposite side to get things back level again. And you can actually calculate this. And the formula looks a little bit funny. It looks more like a classic math formula because they use the symbol pi, but it's pi equals n mRT. But pi doesn't mean pi like in math. Instead, this is the osmotic pressure. So like I said, the amount of force that would be required to get things back level again after it's reached equilibrium would be the osmotic pressure. N is kind of like the N value that we just used. This would be the number of moles solvated. So how many different pieces did things break up into in solution? Was it just one thing, meaning was it unbroken, or did it break up into 2, 3, or even 4 things? And then M over here is just molarity. That's our concentration unit. R is actually similar to the R we saw in our ideal gas law. This is the gas constant. All right. And then the gas constant can vary. A lot of times it depends on what pressure you're trying to measure out in. So there's a gas constant in atmospheres, there's a gas constant for torr, things like that. So we just need to make sure that we use a gas constant with the correct pressure unit. And then T is the temp. And all gas constants typically deal with temp that is measured in Kelvin, right? So I'm not going to go ahead and do a full practice problem with this since it's just basic math, but there are a handful of them in the book, and I would encourage you to try some of them out yourself. All right, good luck studying.